Hi everybody, I'm coming to you here at the parking lot, as you can see, of our school, and I'm out here for a very specific reason. We're going to introduce the idea of reaction mechanisms. And one of the analogies I like to make to reaction mechanisms is that they're kind of like your drive to school here in the morning. You know, when you leave your house in the morning, and let's say, for example, you take the bus. We know that if you take the bus, on your bus ride here to school, there are parts of that drive that go really quickly. You know, you get down the street, you take a right-hand turn, you're moving pretty good. But we also know that there's often a part of that drive that's a little bit slower than others. Maybe there's a stoplight, and if you catch the red light, if you need to take a left-hand turn, it's going to take a long time for you to get to school if you get caught at that red light. In a way, that red light becomes sort of a determining step, a determining part of how fast you can get to school. Reaction mechanisms are the same way. They're a series of steps, and often one of those steps is kind of that crucial feature that determines how fast a reaction can go. So by way of introducing reaction mechanisms here, I want to give you a few terms. What is a reaction mechanism? Well, you've seen us refer to the hills in the reaction coordinate diagram, and a reaction mechanism really is a hypothetical pathway. How do reactants turn into products? Now, we're going to base these mechanisms, which really are just proposals. You can never prove a mechanism. That is, mechanisms are always underdetermined. You come up with an idea, but you can never definitively say that it's absolutely correct. You might have a lot of good data, you might have a lot of good reasons as to why you think it's true, but you can never absolutely positively prove a mechanism. It's always, the fancy term is, underdetermined. And so how are you going to make your mechanism? How are you going to base your ideas? Well, of course, you're going to base them on experimental data. And one really key point of the experimental data is that your reaction mechanism is going to have to match the rate law. And we'll get into the details of that as we look at some examples. Why do we care about figuring out a reaction mechanism? Well, probably the biggest reason we care about it is, well, maybe one, it's kind of interesting. But in terms of actual utility, well, we can improve the efficiency of some reactions if we understand their mechanism. We might be able to make them faster. We might be able to have a reaction transpire in a way that generates less waste, and so that would be good for trying to green our chemistry. So efficiency is a really good reason why we care about mechanisms. Now, in the next couple of videos, as I introduce some specific examples of mechanisms, I'm going to start to use some terminology, including elementary step, intermediates, rate determining step, and a word that sounds like I'm totally making it up, but I'm not. It's called molecularity. So you're going to hear and see me use these terms throughout the next couple of videos, so I want to show them to you now so that you start to get used to them. All right, so again, a reaction mechanism at the end of the day is just a hypothesis. It's our idea as to how reactants turn into products. If it's a really good mechanism, it's going to be well supported with experimental data, and it's going to help improve the efficiency of what we're trying to do. That's all from now.